My name is Gary Petco, your Knox County Schools Mathematics Supervisor, and I'm here for week 6, 7th grade KCS Safe at Home Mathematics video. This week we're talking about expressions and equations. This video can be shown at PBS station on Tuesday. 7th grade starts showing at 1:30, then I believe they do a loop. Your other videos from other grades are throughout the day, and your other subjects are throughout the week. This video will also be seen online at the KCS Safe at Home link from the website, where you find the resources for not only with this video, for the packet, but many other resources that we may have available to you. This video again goes along with the week 6 packet that you could either get online at this time or possibly pick up at the meal distribution sites. Today, we're going to introduce the week's topic like we have in the past, present what tasks are in your packet, kind of work through that task, and then remind you of some extra available student resources that can help you not only with the math involved in this packet, but also for future math problems. This week, as I said earlier, is revolving around expressions and equations. It's Module 6. It's probably what you started working on right before spring break in your 7th grade. It is the 7th grade standard 7.ee.b4. And as a reminder, that just means it's a 7th grade standard. It's EE stands for expressions and equations, and there's a cluster of standards that all revolve, or a cluster of topics revolve around expressions and equations. This is the second cluster. We call it the B cluster, and it's the 4th standard within there. So that means there's a lot of topics revolve around this. This is pivotal as you start your algebraic career, algebraic from topics from 7th grade, 8th grade, on into high school. But this standard is use variables to represent quantities in a real world or a mathematical problem, and construct simple equations to solve problems by reasoning about the quantities. We've got the words variable and equations highlighted because we're going to talk about those. You may have seen them at some point in your math career, but we're going to revisit that and see what it means for today. A lot of our work revolves around work that the great mathematician Carl Friedrich Gauss did. You can see him in the bottom right-hand corner of your screen. He lived from 1777 to 1855. Many consider him the prince of mathematics. He's the modern-day father of algebra. The other mathematicians way before him kind of brought on the concept of algebra, the study of the unknown, but he kind of formalized it in our later centuries. So many things he did, but the biggest thing that he did was he created what's called the fundamental theorem of algebra. You'll learn it in Algebra 2, but it essentially says any equation can be solved, and he's found a way to solve any equation no matter what the solution is. So the work you're doing today is just the surface of what he started on. So we have a lot to work on, a lot of fun stuff to work on, and I encourage you to look up Carl Friedrich Gauss. He had a lot of interesting things that he did in his life. Great mathematician. As I mentioned earlier, the key vocabulary. Let's start with variable. Variable is something you learn in the 6th grade. Variable means changeable to me because in math, a variable, we usually use a letter or a symbol that represents a number. So a letter is used because the number is unknown and it could vary. I mean, we could put any number we want to in that. Way back in kindergarten, 1st grade, 2nd grade, it was a box or a blank that you put. But as you got formalized in your math career, we substitute that box or that blank for a letter or a variable, and we can vary or change what we put in that. And what we put in for that variable, what we substitute in for that variable or that letter, changes the value of the expression or the equation. So we use a variable. In your mathematics, through most of your career, up to at least Algebra 2, you're going to use just your normal letters from your alphabet. Once you get into calculus and beyond, you'll start using the Greek alphabet. Really interesting stuff, but a variable means changeable, means it's a letter that we can vary what we put into it. Okay. The other key piece of vocabulary is an equation. Equation, a mathematical sentence that shows two expressions are equivalent. We've talked about expressions in the past, but when you have two expressions that are equal, now we've got an equation. This showed up in section 6.1 in your textbook. And how this evolved, earlier in your mathematical career, maybe 1st, 2nd, 3rd grade, you had equations that looked like this. 6 plus 7 equals 13. That says these two things are equal. The 6 plus 7 is equal to 13. They're equal quantities. And then it evolved into the 5th and 6th grade where we replaced one of those numbers with a variable or a letter. 6 plus n equals 13. And your task was to say, what do I substitute in for that letter n to make those two expressions equal, to make that a true statement? 6 plus blank equals 13. Now what we're doing in this grade is we replace it even more. We say 2 times some number plus 7 equals 13. This middle one is what was called a one-step equation because you take one step to solve it. Now we're doing a two-step equation. It means it takes 2 steps to solve it. And what we're working on today are applications of equations that you would use this to find out, how do I use this to actually solve some of the problems out there in a contextual situation. That equation I mentioned talked about being equal. It comes from the Latin word equiate. Now, you probably learned in some of your English classes that whenever you have a suffix, T-I-O-N, that usually means the action of the verb. So in our case, think of, you see T-I-O-N, but before that you see a form of the word equal. So the action of being equal. T-I-O-N is the action of whatever word comes before it. The action of being equal. It's usually when you see a word with a T-I-O-N, that means it's probably come from some Latin form. And the Latin form, that's where equation came from. Equiate to means make equal. The action of making things equal. A mathematical sentence that shows two expressions are equivalent. Again, I love looking at the breaking the vocabulary down, looking at the history of it, where it came from, what does it mean? Because if I can break those little root words down, I might have a better understanding of it and also remember it a little bit more. So let's get started with solving contextual problem. Remember, contextual, some people think of it as like a real world problem, but I think it is just in the context of everyday life. Let's see what you've got in your package. You have 2 sets of problems. You have what's called a spark your learning, and then you have a performance task. We're going to look at the spark your learning first. So if you don't want to see the answer yet, you might want to stop the video, work the spark your learning, and then you can pull the video back up and we'll go over the answer. The problem, applying 2-step equations to solve real-world problems. This one was dealing with the perimeter. A diagram of a rectangular sitting area in a botanical garden is shown. A botanical garden, just a garden with plants in it. And they've got a setting area that you can sit in and just view the beautiful plants. And then they tell you the perimeter of it is 60 feet. And as a reminder, perimeter means the distance around a shape. So the perimeter is 60 feet. And they told you the length of one side is 10 feet. They want you to find this longer length right here. They've told you this width or this side is 10 feet. Could you find that given the 60 perimeter? We've got another beautiful mathematician who's going to help us out. I'm kind of biased towards this beautiful mathematician. Her name is Charlotte. She goes to Bearden Middle School. It just happens to be my daughter. And let's see what Charlotte has to say about solving this problem.
Hi, my name is Charlotte, and I'm going to be a 7th grade student at Bearden Middle School. Today, the problem is a diagram of a rectangular sitting area in a botanical garden is shown. What is the length of the sitting area in the garden? So I know that my total perimeter is 60 feet, and that one side of my width is 10 feet. And so I'm going to go ahead and write out my equation. P equals L times 2 plus width times 2. But I know that my variable comes after my coefficient, so I'm going to rewrite this as P equals 2L plus 2.
Okay, I'm going to pause it right there because that's the formula you learned in 5th and 6th grade for the perimeter of a rectangle. As Charlotte so eloquently put it, it's 2 times the length plus 2 times the width. Because we know a rectangle has congruent sides that are opposite. Okay.
So I know that these 2 sides are congruent, which means they're equal. So I know that this equals 10 feet also. Adding that together, your total width, 20 feet. So I'm going to add what I know into my equation. So my perimeter is 60 feet equals, don't know the length, plus 10 times 2, or you can just say 20. Now you have to find the total length. So I'm going to subtract the total perimeter by the total width to get the total of 40. So now I know that 40 is the total length. I'm going to add here. But I need to find what one side of the length is. Since I have two sides of congruent pairs, I need to divide this by 2, which means one side is 20 feet, and the other side is 20 feet, meaning total equals 40 feet. Now I can plug that into my equation, saying 60 equals 2 times 20 plus 20, or 60 equals 40 plus 20. Thank you.
Okay, I love how Charlotte reasoned it out. She said, this is what I know. I know I got 60 feet around, and I know that I'm dealing with a rectangle that where the opposite sides are congruent or the equal. So if one side is 10 feet, the opposite side must be 10. So that's total of 20 feet out of the 60 I already know. So that gives me 40 feet left over. And out of that 40 feet, that's the total amount left over for the other two sides. But if those two sides are equal, then I split that 40 in half, so I get one side's 20 and the other side's 20. Charlotte, great job, and I look forward to seeing you being a math teacher and a future math supervisor one day. Thank you so much. Okay, now we're going to go on to the performance task. Again, this is a 4-part task. You might want to stop the video, start working the task, and then come back and look at the answers. You also have the answers in your packet if you would like. So let's see what happens with this one. We've got a mechanical engineer. Mechanical engineer is testing the amount of force needed to make a spring stretch a given amount. The force, called Y, is measured in units called newtons, abbreviated with the capital letter N. The stretch X is measured in centimeters. Her results are shown on the graph. So you notice we've got the stretch of the spring in centimeters. So as the spring stretches different amounts, the force changes. That must mean if it's think about that if you got a slinky or a spring and you put a weight underneath it. The more it stretches, it's probably stretching because there's a heavier force or a larger force on it. And that kind of makes sense. So those two things are related. The amount of stretch in the spring to the amount of force put on that spring. And that can be visualized right here with this graph. And it looks like it's increasing, which would make sense. The more the spring stretches, the more force must be on it. And we're using the letter N for the units called newtons from Isaac Newton, and we're letting the letter Y be our force be our Y variable and stretch be our X variable. Okay, that sets the problem up, and let's see what they're asking in part A. Write an equation for the line. Explain using the graph and using the equation. Why is this relationship proportional? Now, what we learned in previous units, we learned that a proportional relationship can be modeled or visualized. Modeled or visualized, kind of the same thing. How can we visualize what's going on here? By a graph of a straight line that goes to the origin. So we know it's a proportional relationship if it's a straight line that goes to the origin. Well, look at this line. It's a straight line, meaning it doesn't curve. And does it go to the origin? Well, it should have started the origin 0, 0, and I made a table of values for some of the points on that line. I made the table down here. So you got the point 0, 0. You also got the ordered pair 2, 16. Another ordered pair, when the x is 4, the y is 32. When the x is 6, the y is 48. So it's a straight line, it goes to the origin. So that's how we can explain using the graph. If it is a straight line that goes to the origin, then it's a proportional relationship. But how about using the equation? We also know that if it is that straight line, then the equation comes in the form of y equals k times x. Now remember that from last week, k times x. K is our constant of proportionality. where k does not equal 0. Now that makes sense because let's face it, if k were 0, what if k were 0? What is 0 times x? Well, that's 0. So y equals 0. That would not give us the type of line we have. That would give us a different type of line. That would give us a horizontal line. So if we have an equation in the form k times x, where k does not equal 0, then we've got a proportional relationship. Remember from last week, we had to find what k is. You find k when you have the relationship y divided by x, and that stays constant. Therefore, they're called the constant of proportionality. Let's see if it's constant. If I take 16, which is a y value, and divide it by its corresponding x, I get 8. If I take 32 and divide by its x value, I get 4. 32 divided by 4 is 8. 48 divided by 6 is 8. So that's staying the same or staying constant. That is the value of k, whatever that constant value is in our relationship. So therefore, the equation, since it starts at 0, 0, it's a straight line, the constant of proportionality is 8. The equation is y equals 8x. Write an equation for the line, which we did. Use the graph. The graph, since the straight line goes to the origin, shows the proportional relationship. The equation shows the proportional relationship because it fits the form y equals kx, where k is some number other than 0. So our equation, y equals 8x. Now keep that in mind because we're going to use it in future problems in this performance task. Okay, let's move on to B and C because they kind of go together. B says identify the rate of change and the constant of proportionality. And then C says what's the meaning of that constant of proportionality in the context of this problem. Wonderful questions. I love this because this really puts it to what I call real life, puts it into meaning. So let's see, identify the rate of change. Just break that down. We got it in green. Rate of change. Rate, or how fast something is changing. And in math, we describe that with a number or numerical amount of quantity. So how fast is this changing? It's changing if 8 newtons every centimeter. If I go back to that previous slide, every time I go up a centimeter, my graph goes up 8 units, meaning I go up, my force is 8 units every time I go an extra centimeter. At 16, I go to 2. At 24, I get it 3. 32, I get it 4. So in other words, the rate at which this is changing, there's 8 newtons for every centimeter. And as a reminder, the great part about this concept, we have so many things that are similar. The rate of change is the same thing as the constant of proportionality in here. So our constant of proportionality, which we call k, is that value 8. But what is the meaning? Oops, let's go back to that. What is the meaning of the constant of proportionality in the context of this problem? In other words, tell me what that 8 means in reference to this problem. 8 in per centimeters means every centimeter stretch of the spring requires 8 newtons of force. So every time that spring or that spring stretches an extra inch, that must mean 8 more centimeters of newtons of force was put on it. So if it stretches 2 centimeters, 16 newtons. So it allows us to know, just by looking at how much the spring is stretching, how much force must be put on it. Interesting question. Okay, part D. I believe this is the last one. The engineer applies a force of 41 6/10 newtons to the spring. Now we had an equation for it. Let's see how will it help us. Write and solve an equation to find the corresponding stretch in the spring. So that's saying, what if I give you the amount of newtons? If I'm going to put a force of 41 6/10 newtons on this spring, how far could I expect it to stretch? That would be something engineers want to know, because they want to know how, there's something called the elasticity of the spring. How much can it actually stretch? So if I put a big force, how far is that spring going to go towards the ground or towards in a vertical direction? So let's see how we do that. We'll work it here and then we'll discuss it as we solve it. As always, I'm going to read the problem. I'm going to underline key words. I've got 41 6/10 newtons in there. I've got write and solve, 2 steps, just write and solve an equation for the stretch. Now, as a reminder, our newtons, our force is y, and our stretch is x. If we remember, from part A, we had an equation that described this. From part A, we had that equation, y equals 8x, where y was newtons, x was stretch. So I'm going to use that equation with this information to find my answer. So write and solve an equation. There's my equation. Y equals 8x. Now let's solve the equation to find out how much stretch if I have a force of 41 6/10 newtons. All I'm going to do is substitute the 41.6 in for the y value that I'm given. And I'm going to solve it. That's a one-step equation where I divide both sides by 8 because I have 41 6/10 equals 8x. And if I divide 41 6/10 by 8, I end up with a value of 5.2 centimeters. 5.2 centimeters for the stretch. So if it stretches 5.2 centimeters, that must mean there was a force of 41.6. All right, great question. All right, let's move along. As a reminder, if you need additional resources, please rely on our great friend Ernie Roberts. He's on Mathline, the PBS station, every Monday through Friday, 6 to 6:30. The PBS station. The phone number is 1-844-NUMBER-8 or 686-2378. Or you can connect with him Math Online on Facebook. He's there throughout the whole year, summer, school year, for any of your math problems with here or ones that you would have in your homework. Ernie Roberts is a great resource to help you with not only these problems, but any future problems you may have. Additionally, over the summer, you and your folks, parents, guardian, significant, your grandparents, aunts, uncles, brothers, sisters can use this chart to help you look for math all over the place. Look for shapes and patterns in life. Measure ingredients in making a recipe. Explain the math skills you're working on in school. A lot of great resources. Excuse me. All right. And one more reminder, this video can be seen online, but it also can be seen on our PBS station on Tuesdays starting at 1:30. Folks, I've enjoyed working with you. Please don't forget to go to our Knox County Schools website for your student resource for this packet and others. We'll have some summer work coming up in the next few weeks. This is our last video, and I'm sad to say that. Our last video of our packet. We've had 6 of them. I've had an incredible time, and I thank you. And I look forward to seeing you maybe through the summer and through the school year. Thank you so much, and good luck in your math career.